Okay, some more notes for section 7.3. And this is example 3. Find the volume of the solid form when the region bounded by y equals 2 minus x squared and y equals 1 is revolved about the line y equals 1. Okay, so we have these two curves, and this is y equals 2 minus x squared. Again, 2 minus x squared is the same thing as negative x squared plus 2, so it's just a parabola, okay, shaped in the negative direction because it's negative, shifted up 2. So that's this parabola, y equals 2 minus x squared, and then the line y equals 1. And we could just set these equal to each other, and we actually find out that they intersect at x equals plus or minus 1. So those are the intersection points. So we're just talking about this region here, the top here. Okay, and we're going to revolve that region. I should probably put a line underneath it. So this is the region here, and I'll enclose it in green so you can see it a little bit better. And this region I'm going to revolve about this line y equals 1. So it's going to form kind of like an egg type form here. So again, we're going to use the disk formula. And remember, the volume is going to be pi r squared. That's the area times the thickness of the little disk, which will be dx. So the area is pi r squared because it's a circle. It's a disk, circular disk. Now, how am I going to find the radius? In this case, it's not going to be the value of the function because that would give me this whole thing. I just want this length. So this is where we can use top curve minus bottom curve, top curve minus bottom curve. And you can do an intuitive approach, and then you can kind of use this as a backup to check these. In other words, if I want to find the height of this radius, that would be from here to here would be that would be the y actually, 2 minus x squared, but then I want to subtract from here to here. All right. So I'm going to find that this distance by taking the whole distance, which is from the line or the x-axis all the way up to the function, and I'll subtract this distance, and I should get that distance. And it's real easy. It's usually top curve, which gives me the whole thing, minus the bottom curve, which gives me that distance, gives me the remainder, which is my radius. So that's top curve minus bottom curve, and the bottom curve is just y equals 1. So that makes it nice. So top curve minus bottom curve, that's my radius, and remember my area of my disk will be pi r squared, and this is the thickness of the cylinder, or the height of the cylinder, and I'll add all these up from -1 to 1. Now this is symmetrical. It's an even function. You can see the right side and the left side of the y-axis is the same, so we can reflect it around the y-axis. So this is a handy little trick you want to do. Rather than integrating from -1 to 1, I took out the pi, but I can also just make this 2, just double it and go from 0 to 1. So that's going to save me a lot of work because the zeros work out nicely many times. So I just took out this, I doubled this to make it 0 to 1. And then I have left, if I take this is going to be 2 minus 1 is 1 minus x squared squared. So this is my nice form of the integral. And then just with a 2 pi, I take the antiderivative of x is x. The antiderivative of 2x squared is 2x cubed over 3, and then plus x to the 5th over 5, and I'm going to evaluate that from 0 to 1. And look what happens when I evaluate it at 0. 0, 0, 0. I've got factors of 0 in each term, so those just disappear. So I just have to take the 2 pi and evaluate this at 1, and then multiply it. So I've got 1 minus 1 cubed is just 1, so 2/3, and 1 to the 5th is 1, 1/5. I can put this all over 15, so I got 15 over 15 minus 10 over 15 plus 3 over 15. And 15 minus 10 is 5 plus 3 is 8, so I got 8 over 15. This is 8 over 15 times 2 ends up being 16 over 15 pi. I hope you can read that. I was running out of room. Okay? But we can do this all arithmetically, analytically, no calculator. So it's good to be up on that. Okay? And then 3b, example 3b, is the same region now, except we're going to revolve it about the line y equals 0, and now we're going to use the washer method. Okay, and remember this was the washer method, volume and pi, and then we just factored out the pi. So basically we've got the big radius minus the little radius, and in essence what we're going to do is we're going to take this whole kind of it's kind of a flattened egg type thing when we revolve it around here, and we're going to subtract this inside part, which is a cylinder. So we're going to cut a cylinder out of it. It's almost like if you have a big marble and then a big odd-shaped marble, and then you're going to drill a cylinder out of it. So that's what you're going to do. Okay. So we have to find, and that in essence what we're doing when we look at the washer method. We go back at your main notes up here. This was the washer method. This was the whole object. In other words, if you separated this up into two integrals, basically you're taking the volume of the total object and then you're subtracting the volume of the inside. So that's where we get that minus. So again, it's like the whole thing, and we're going to drill out the inside or subtract it. So how are we going to find all these radii? Well, again, the radius of the whole object, which is capital R, that's going to be just my value of the function. So this is going to be given by 2 minus x squared. And then the little r is going to be the inside curve, or the bottom curve. So again, this is going to be like this. So that would be just 1 minus 0, which is just 1. Now in each case you can think of these as top curve minus bottom curve. I did this over here. The big R is the top curve and the bottom curve is 0, so it's just top curve minus bottom curve. That's going to give me this. And for the little r, it's going to be top curve, which is 1 minus 0, again, bottom curve. Okay, and we can have variations on this, but you still want to use this technique to get your radii, because those are the tricky parts. Okay, so now we have big R and little r, so we're ready to just go to mechanical work. The rest is mechanics. Okay, so it's just setting these things up. So I hope this makes sense to you, how we're revolving this around, and how we are using the washer method, because we do have a hole in it, and how we determine the big R and the little r. Okay, and again, the object we have is ending up being this part, but it's going to be revolved around there, so I guess I could. And close that in blue, so that's going to be the part that's going to be revolved around, but there will be a hole there because it's offset from the line of revolution. It's revolving around the x-axis, which is y equals 0, not y equals 1. Okay. All right, then once we have the big R and the little r, and we've factored out the pi, then again I'm going to do the same technique. I'm going to, since it's symmetrical, again we've got the same symmetry, I can change this from -1 to 1 to just 0 to 1 and double it, and there's the pi, and then I can work this out. So this is going to be, I've got to square this out, so it's going to be 4 minus 4x squared plus x to the 4th, and then 1 squared is 1. Then I can simplify that when I take the antiderivatives. So what's 4 minus 1? 3, and the antiderivative of 3 is 3x, and this is going to be 4, x cubed over 3, and this could be x to the 5th over 5 again. And again, look what happens with the 0. Each term has a factor of 0, so the 0 part goes away. So my f of a is 0. My f of b is this all evaluated at 1. So that's going to be 3 times 1, 4/3, 1/5 minus 0. And then again, we'll make these all factors of 15, or I'm sorry, all fractions with denominators of 15. So I can add them. And again, like I said, the f of a, the second part is 0. That's nice. Okay, so I've got 45 over 15, 20 over 15, 3 over 15. And that's 25 plus 3 is 28 over 15 times 2 pi, and that ends up being 56 pi over 15. So again, we can do it, leave it in terms of pi. Don't need a calculator. Okay, so that's a good example of the washer method. I hope that helps.